All right, now we're going to look at more complicated differential equations than we have before. And first, we're going to examine ones that look like the following. So I'll have, let's say, some sort of a function of x. I'm going to put an index to indicate what I'm talking about. So a sub n of x, and I want it times the nth derivative of y with respect to x. And then another a sub n minus 1 of x times the derivative, the n minus 1th derivative of y with respect to x, all the way down until, say, a sub 1 of x times dy over dx plus a sub 0 of x times y. All of that's equal to 0. If that's the setup, then this is referred to, or this is called, a homogeneous linear differential equation. Homogeneous because the entire thing is set to 0. Linear because if you want, you can refer to these a sub whatevers as coefficients, if you will. So each of these is a function of only x. Notice that the derivatives of y are straight up given, nth derivative of y, n minus 1th derivative of y, all the way down to the first derivative and the 0th derivative of y. So another way you could write this equation that I have looks something like this. A sub n of x times y, and then if we put the n in parentheses like that, I know it's the nth derivative of y, plus a sub n minus 1 of x times the n minus 1th derivative of y, until I get down to a sub 1 of x y prime plus a sub 0 of x times y, and all that's equal to 0. So we're linear since the coefficients are functions only of x, and also these are the derivatives of y all the way up to the nth order, and you don't see any of these derivatives being raised to powers or anything like that. So it looks very much like a polynomial in regular math. We're going to examine these for a little bit and then see how the solutions compare to a general one where this side is not the right side is not necessarily equal to 0. I will say this: if these coefficients are all continuous functions and all these derivatives exist, and they could be 0, then you're guaranteed to have solutions to an equation such as this. So, and there's more to be said than just that. Let's start with an example and I'll show you what I mean. Alright, so we're going to start with this equation. Y double prime minus 3y prime minus 4y equals 0. Now, right now we're not going to determine what the solutions are. We'll be giving them to you and show you that they work. So here we have y1 equals e to the 4x is a solution. How do I know? Well, I'll plug it in. So if I try to go y1 double prime minus 3y prime minus, now this is y sub 1, minus 4y1, I'm going to plug those things in. This e to the 4x. So I have e to the 4x double prime minus 3 e to the 4x prime minus 4 e to the 4x. And let's just work this problem and see what happens. Now I'm going to do the derivative first. The derivative of e to the 4x is 4e to the 4x. And I have minus 4e to the 4x. The reason why I did this first, because I got to calculate a second derivative. If I do this derivative again, I'll get 16 e to the 4x. And then just a little simplifying will show you that it comes out to be equal to 0. So 16 e to the 4x minus 12 e to the 4x minus 4 e to the 4x. Of course, that equals 0. So that's one solution to the problem. Another solution is, we'll call it y sub 2, that equals e to the negative 4x. I'm sorry, e to the negative x. So you plug it in and make sure that it works. So these are both solutions to the problem. Now, we also have y1, I don't know if I want to call it y1, but let me erase this and I'll say we also have that y equals c1 e to the 4x is a solution. You can see that by when you plug it in, if I have y double prime minus 3y prime minus 4y, and I plug this stuff in here, I'll get c1 e to the 4x, that'll be double prime, minus 3 c1 e to the 4x prime minus 4 c1 e to the 4x. Well, what's going to happen here is the c's will completely not be touched by any of these derivatives. When I take this derivative, for instance, the second derivative of the first part, I'll get 16 c1 e to the 4x. And as before, the middle piece, I'll get negative 12 c1 e to the 4x. And then I'll finally get minus 4 c1 e to the 4x. Well, I can factor c1 out of absolutely everything. So this is a solution too. We also have c sub 2, of course c is just a constant, e to the negative x is a solution. And this is for any constant c1 or any constant c2. In fact, y equals c1 e to the 4x plus c2 e to the negative x is also a solution. For any constants c1 and c2. So if you try to plug them in there, let's see, we have y double prime minus 3y prime minus 4y equals 0. Plug in this entire expression. I'll get c1 e to the 4x plus c2 e to the negative x double prime minus 3 c1 e to the 4x plus c2 e to the negative x prime minus 4 times c1 e to the 4x plus c2 e to the negative x. Well, when you take the derivatives, second derivative, once again, the c1 and c2 are unaffected. If I take the second derivative of the first part, I'll get 16 c1 e to the 4x. And the second piece, when I take the derivative e to the negative x twice, it's just e to the negative x again. So plus c2 e to the negative x minus, now here, when I take the derivative of this, I'll get c1 e to the 4x. So when I take the derivative, I'll get c1 times c1, or 4c1 e to the 4x. So I'll get negative 12 c1 e to the 4x. And then I'll have, when I take just one derivative, I'll get negative c2 e to the negative x. So I'll get positive 3c2e to the negative x. And then finally, for the last piece, I'll get, just leave those alone, negative 4c1e to the 4x minus 4c2e to the negative x. And then when you look at these, I've structured it like this so that you can see that what I have is c1 times 16e to the 4x minus 12e to the 4x minus 4e to the 4x. Of course, all that stuff is just 0, plus c2 times e to the negative x plus 3e to the negative x minus 4e to the negative x. So you can see here that all this stuff inside of here is 0, and all this stuff inside of here is equal to 0 as well. So this is c1 times 0 plus c2 times 0. So that's the nature of differential equations. Whenever y is a solution to a homogeneous differential equation, then cy is also a solution for any constant c. And you saw if I got multiple solutions, I can do a combination of constants multiplied or used as coefficients for them. Remember, homogeneous means that the equation is set equal to 0. Now let's talk about initial values. So once again, we could look at the same equation I had before, y double prime minus 3y prime minus 4y equals 0. And I'm going to introduce an interval that this is valid for, from negative infinity to infinity. Whatever solutions I'll get will work for the entire interval. In fact, we already found them. We have our solutions. y1 was equal to e to the 4x. y2 was equal to e to the negative x. We're both solutions. Now, suppose we were to solve y double prime minus 3y prime minus 4y equal to 0, subject to the initial values and suppose I gave you y of 0 equaled 1 and then y prime of 0 equals 2. So suppose I gave you that much information. Well, here's what we do then. We know that y equals c1 e to the 4x plus c2 e to the negative x is a solution. Well then, if I wanted to satisfy these initial values in order for y to satisfy the initial conditions, we need y of 0 to equal 1. So if I replace x with 0, So y of 0 equals 1. This gives me the equation. I'm going to replace x with 0. c1 e to the 0 plus c2 e to the 0 equals 1, which is the same thing as c1 plus c2 equals 1. Now, on the other hand, we have y prime of 0 equals 2. So, let me take derivatives here. Y prime will equal 4c1 e to the 4x minus c2 e to the negative x. And then we plug in 0, so y prime of 0 equals 4c1 minus c2. And we know that's supposed to be equal to 2. So I get 4c1 minus c2 equals 2. Now then, I want to solve this system of equations for c1 and c2. So I have c1 plus c2 equals 1, whereas 4c1, I think that I just made a mistake. No, I did not make a mistake. I'm all right. Minus c2 equals 2. Well, one way to get c1 is I could simply add these two equations together. I get 5c1 equals 3, or c1 equals 3/5. On the other hand, let me rewrite these equations again. This time I'll notice I wiped out the C2s in my first effort. I'm going to wipe out the C1s in my next effort by simply multiplying the first equation by -4. And that gives me a system -4c1 minus 4c2 equals -4. And in the second set, I have 4c1 minus c2 equals 2. And I'll do like I did before. I'll add them together. The c1s will wipe out, and I'll have -5c2 equals -6. So c2 equals 6/5. So in order to solve this particular equation, since I have initial values, y of 0 and y prime of 0, since I have those, I'm able to figure out the c1 and c2. So the solution to y double prime minus 3y prime minus 4y equals 0 on the interval -infinity to infinity, where y of 0 equals 1, y prime of 0 equals 2, is this formula. My c1, I had 3/5 e to the 4x plus 6/5 e to the -x. So that's sort of the nature of what we're going to do here. We are going to solve general equations. Let me scroll back up to show you what I'm talking about. We're going to solve general equations like this, and then we're going to talk about initial values and whatnot. And so once you throw in initial values, that's when you're going to be able to solve for your C1 and your C2. Notice also that on the interval from -infinity to infinity, since e to the x is differentiable absolutely everywhere, we can see why the solution might be valid on all of -infinity to infinity. How do we know that is the only solution? I mean, how do we know it's unique? Well, that all has to do with solving the system of equations that I had there. It has really to do more with the system of equations than anything else. Like, for example, if you were to solve the following: ax plus by equals 0, cx plus dy equals 0, there's only one solution, assuming that this thing is able to be solved at all. What I'm talking about is you have three possibilities. You have a unique solution, and you also have the possibility of an infinite number solution. There's possibility of no solution at all. Well, if I want to try to get a solution at all, the first thing I might try to do is wipe out the x's by multiplying the first equation by c and the second equation by negative a. That will produce the equations acx plus bcy will equal 0, and negative acx minus ady equals 0. When you add these two equations together, we can see that the x's cancel, and I get bc minus ad y is equal to 0. Now, the only way for y to equal 0 and to be a certain answer is if this piece here, this bc minus ad, is not equal to 0. Well, so we need ad. I'm going to take its negative instead. You'll see why in a minute. We need that quantity not to equal 0. Then I can divide by it and actually get y equal to 0 as my answer. If it wipes out everything, then that's no good. So this quantity here, you may have seen it before. Let me go ahead and put the numbers up. A, B, C, D. When I put absolute values like this, and that's really not what they are, when I do this, I'm actually looking for the determinant of what's called a 2 by 2 matrix. And the formula for such a thing as this is I multiply A times D, and then I subtract BC. So basically all I'm saying here is these kinds of equations, where did it go? This kind of a system of equations will have a unique answer of 0 if the matrix is not equal to 0. And then, continuing on, I can do ax plus by, let's just say equals some number z, call it z1, and cx plus dy equals z sub 2 has a unique solution if AD minus BC does not equal 0. Well, that's kind of interesting. Here, your answers won't necessarily be zeros, probably not, if Z1 and Z2 are not 0. But it still relies on this determinant quantity not to be equal to 0. And I can play the same game I did before when clearing out x's or y's. You'll see I'll be able to solve for y or solve for x, and this thing will pop up in the denominator of something if you divide out to get your answer. Look at our problem. The one that went y double prime minus 3y prime minus 4y equals 0. And we needed that y of 0 equals 1, y prime of 0 equals 2. y1 equal e to the 4x, y2 equal e to the negative x before. These were the answers that we had, and these were the numbers that they had to satisfy. Well, our general solution looked like this. Y equals C1 Y1 plus C2 Y2. And we needed that y of 0 would equal 1. So y of 0 was 1, so 1 equals C1 Y1 of 0 plus C2 Y2 of 0. Now additionally, we needed that y prime of 0 would equal 2. In our case here, then if I take, I'm not going to go back and put those in. I don't even know why I listed it here. I really don't need them for this discussion. But when I plug a 2 into this, I then have C1 y1 prime of 0 plus C2 y2 prime of 0, and that's got to equal 2. So now let me go ahead and throw this in to a system of equations. So I'm going to write it in a strange way here. I'm going to write y1 of 0 times C1 plus y2 of 0 times C2, and that equals 1. Then we have y sub 1 prime of 0 times C1 plus y2 prime of 0 times C2 equals 2. As before, I'm going to be able to solve this for C1 and C2 if that determinant does not equal 0. This has a unique solution if y1 of 0 times y2 prime of 0, so y1 of 0 times y2 prime of 0 minus y1 prime of 0 times y2 of 0 does not equal 0. Or in other words, if this thing, y1 of 0, y1 prime of 0, y2 of 0, y2 prime of 0 does not equal 1. I'm sorry, does not equal 0. I don't know why I said 1. Does not equal 0. And I'll be able to do all those tricks I showed you before in order to figure out what C1 and C2 is. And the answer will be unique as long as this derivative, or this determinant, does not equal 0. Now, for each x in I, where I is an interval containing a solution. We can solve any differential equations with initial values let's say we have y, let's call it of x naught equals y1 and y of x naught. I'm going to call it y prime of x naught. I'm going to instead use a different letter. I'm going to call it k sub 2, and that y1 is going to confuse me with the other stuff. K sub 1. Let's say if y1 and y2 are solutions, then we'll get a pair of equations C1 y of x sub 0 plus C2 y of x sub 0 sub 1, 2, and that will equal, say, I don't know, some value. I don't want to call it k sub 1. because it may not equal. It would be ck sub 1 plus, well, since this is supposed to be k sub 1 and this is supposed to be k sub 2, we'll have c1 plus c2 k1. I don't care about that number. Give me a second here. c1 y sub 1 prime of x sub 0. So if I got to take the derivative in order to try to satisfy this thing, plus c2 y2 prime of x sub 0. And that then will equal c1 plus c2 times k2. And just as before, if I want to figure out what the c1 and c2 are, they're like our unknowns in this thing, then we will need the following. y1 of x sub 0, y2 of x sub 0, y1 prime of x sub 0, y2 prime of x sub 0. This thing is not to equal 0. Now, if I want a solution for any x in I, then if I want to get a solution for every single one of these, I will need y1 of x, y2 of x, y1 prime of x, y2 prime of x. That quantity will not equal 0 for any x in I. So let's go back to my example. Let's take a look at what we had. When we had this equation to solve, I indicated that we had two solutions. y1 equals e to the 4x, y2 was equal to e to the negative x. So I need to show that this thing here is not 0 for any possible x from negative infinity to infinity. Remember, the solutions were on the interval from negative infinity to infinity. So how do we do that? Let's plug these things in. I am going to refer to this as w parenthesis y1 comma y2. You'll know why in a minute. So w of y1 comma y2, that equals y, and it's not even, I'm going to drop the x either, because we can just say y1 prime, y2 prime, and we want that not to equal 0. Let's go ahead and throw in my y1 was e to the 4x, y1 prime was 4e to the 4x, my y2 was e to the negative x, y2 prime was negative e to the negative x. And let me go ahead and calculate this thing. So if I multiply across here, I'll get negative e to the 4x times e to the negative x. And I subtract multiplying by the opposite diagonal. So I'll get minus e to the 4x times e to the negative x. So e to the 4x times e to the negative x. And when you multiply e to the negative 4x times e to the negative x, you get e to the 3x. So I get negative e to the 3x minus e to the 3x, and that equals negative 2e to the 3x. I happen to know that does not equal 0 for any x, because e raised to a power is always positive. In fact, if you look at its graph, e is one of those things that shoots up quickly, but it never touches the x-axis ever. So I know no matter what x is, I'll be able to find a solution for any x in any real number x. So we define the Wronskian. And that's where I came up with the W from. That's listed as the determinant of y1, y2, then y1 prime, y2 prime. And that, as I mentioned, for the times we need to calculate, multiply diagonal this way, top left to bottom right, you'll have y1 times y2 prime minus the other way, y1 prime times y2. So many things that we have will count on this thing not equaling 0. Now there's two questions. First, how do we know that y equals c1 y1 plus c2 y2 will contain all solutions? That first one is simple because when I go to make when I look at this y1 prime, y2 prime, y2 not equal to 0. I told you, let's go back to the system we had before. I don't think I'll go really straightforward here. I'll come way back to this right here. If this is not equal to 0, if the determinant's not equal to 0, then this quantity, this thing, will have a unique solution. And it will be the complete solution. Because perhaps, if you remember, you may or may not, that if I had a third solution, let's say y sub 3, then because of the nature of this thing here, I would be able to create a third set of equations, and then I would be able to have a y3 that looks something like this. y1 prime, y2 prime, and then y3 and y3 prime. Well, here, first of all, the determinant of this is not even defined. They only define them for when you have an equal number of columns or equal number of rows as you do columns. Here you've got 2 rows and 3 columns. So you can't even define it. But that's not the most compelling reason why. It's the fact that if you look at just solutions in general, what they call a 2 by 2 system of solutions, let's say z1 equals z2. Once you add a third collection of solutions in here, so it then might look like ax plus by plus, let's call it cz, dx plus ey plus fz, and these might equal z1, z2. If you have more unknowns than equations, then there's automatically going to be an infinite number of solutions to this problem. So you won't have a unique solution because this will be what they call overdetermined. Or there may be no solution, but you will definitely not have a unique solution if this occurs in here. And also, it's the complete set of solutions. It will contain all the solutions because whenever you're trying to solve something like this, if you have any kind of a quantity that looks like this, let's say x, I don't know, xy, automatically will equal 1 times x comma 0 plus 1 times 0 comma y. So any solution or any what they call a vector can be rewritten as something like this. And then if you have any other vector, let's call it zw, that will automatically equal some constant times x comma 0 plus some constant times 0 comma y. which when you put this together, you'll get cx dy. That means you'll be able to rewrite any other vector as a linear combination of these two vectors. So you can't have another solution because your solutions then would not be unique. And it doesn't matter anyways, because once we have two what they call linearly independent vectors, that is what they say spans R2. It spans Euclidean space, I suppose you'd call it, right? That just means that any other vector like ZW can be rewritten as a linear combination of the x and y's. For example, check this out. Z can equal x over x times z, which is equal to z over x times x, and I could call that c sub 1 x. Similarly, w can be rewritten as y over y times w, which is w over y times y, and I could let that be my c2y. So you can see that z and w are linear combinations of this, and you can see where this comes in then. Or actually probably, wait, I called this C, not C, and then I called this D. So, any other solution you get will be a linear combination of the solutions we already have. This is some linear algebra stuff. I can't give a lot more detail than that for right now. But basically what we're going to do is we're going to try to find solutions to the homogeneous system and use those to find other solutions. Finally, we say that y1, y2 is a fundamental system of solutions when the Wronskian of those, y1, y2, which equals the determinant of y1, y1 prime, y2, y2 prime, does not equal 0 for any x in the interval. For example 2, let's show that y1 equals cosine of the natural logarithm of x and y2 equals sine of the natural logarithm of x is a fundamental system of solutions to x squared y double prime plus x y prime plus y equals 0 on the interval, the open interval 0 to infinity. So what I need to show is, first of all, I need to show the Wronskian of these is not 0 for any x's that might on this interval. So let's first do that. So let me first do the Wronskian of y1, y2. That's going to equal y1, then y1 prime, y2, then y2 prime. That's going to equal y1 will be cosine of ln of x, cosine of ln of x, and its derivative will be negative sine of ln of x But the derivative of ln of x is 1 over x. So you'll get negative sine of ln of x divided by x. And then for the y2 part, you'll have sine of ln of x. And the derivative of that is cosine of ln of x divided by x. Well, let's go ahead and calculate just as we normally do. So I'm going to multiply diagonal. I'll get 1 over x. I'm going to write it as 1 over x times cosine squared of ln of x. Then I'm going to subtract this part. So I'll get minus a negative. I'll get plus 1 over x times sine squared of the natural logarithm of x. I'm going to factor out the 1 over x. And I'll get cosine squared of ln of x plus sine squared of ln of x. Well, you ought to know from linear, trigonometry, that this piece inside of here is equal to 1. So this equals 1 over x times 1. And I know that this does not equal 0 because the interval we're dealing with is 0 to infinity. I'm not including 0. So I can see that no matter what the x is, the Wronskian is not equal to 0. Now, in addition to that, to show it's a complete system of solutions, or a fundamental system of solutions, we need to plug them in and make sure each of them works. So I need to take, so let's take x2, y1 double prime. Let me see what the original equation was again. xy prime plus y prime. So then we have x times y1 prime plus y1. And I will replace my y1 by its derivative. So this is the derivative of y1 right here. I'll have to take its derivative. And hopefully you'll remember the quotient rule when dealing with these things. So the quotient rule says, here's the numerator, negative sine of ln of x. I'm going to take the derivative of the numerator, and I'll get negative cosine of ln of x. Chain rule says that I'm going to have over x, and leave the denominator alone, then minus. Now I'm going to leave the numerator alone. So since I have negative sine of ln of x, this becomes plus sine of ln of x. The derivative of x is 1 times 1, and then all of this stuff will be over x squared. So let me go ahead and make this parenthesis bigger. Plus x times y prime. I already had y1 prime. That was negative sine of x, ln of x over x. And then finally plus y1, which was cosine of ln of x. Now I just need all this stuff to turn out to be 0, and I'm all set. The first thing that I noticed when I'm doing this is I could take out the x's here, the x squareds at least. I can also take out these x's. So I'll be left with negative cosine of the natural logarithm of x plus sine of the natural log of x. And then notice that these x's cancel out, and I'll get minus sine of ln of x. And then finally, plus cosine of ln of x. And you can see that all the positive and negatives cancel out, and you get 0. So on your own, verify that y2 is a solution. So your job is to verify that sine of ln of x is a solution. So there we go. So now we know that y, which equals c1 cosine of ln of x plus c2 sine of ln of x, contains all the solutions to the differential equation. Different initial values will give me different c's. That's basically what it is. Now, a general linear homogeneous differential equation will look like a sub n x y to the n plus a sub n minus 1 of x y to the n minus 1, the n minus 1th derivative of y, plus dot 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 plus a sub 1 of x y prime plus a sub 0 of x times y, and that'll equal 0. So that's the way it will look like. The equation will have n linearly independent solutions y1, y2, dot 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 dot, yn, that will form a fundamental set of solutions and the Wronskian of those things, y1, y2, dot dot dot, yn, will equal, and the way we write it is this big giant looking thing like this, y1 prime dot 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 y1 to the n minus 1 of y2 prime dot 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 y2 to the n minus 1, and these will go until you get to yn. Then you'll have yn prime dot 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 y sub n to the n minus 1. This whole big determinant will not equal 0. We'll talk about the determinant of something bigger than 2 by 2 in a minute, but let me just get this stuff down here. So as long as that's not equal to 0, don't forget, the coefficient functions all have to be continuous functions as well. But once we have this stuff, and we have that it's linearly independent, then we'll be able to write the general solution, what they call the general solution, will look like y equals c1 y1 plus c2 y2 plus dot 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 plus cn yn, and that will tackle every possible solution there can possibly be. So because we have n of them, we don't need to have n minus 1 of them. If we have less than n of them, it's probably because something is not linearly independent. Besides these types of equations, a second kind that we'll be looking at, which is extremely related to this, will be the non-homogeneous. But still linear differential equation. The way these things will look is exactly like we had before. You'll have some sort of function of only x as a coefficient for each of these things. and I'll get to the distinguishing feature in a moment. Right there it is. The difference here is non-homogeneous means that the other side is not equal to 0. So I must specify that g of x is not just the 0 function. But the two types are definitely related to each other. Here's how we're going to work. To solve these, we'll first find all of the solutions to the homogeneous version of the equation. So, after that, we'll compute a particular solution. To the non-homogeneous equation. And so it works like this. We'll start with an of x, y, the nth derivative of y. I'm going to really start abbreviating now. So once we solve this equation, we'll have n linearly independent solutions. So we'll get the solution, say y1, y2, up to yn. And then form the complementary. I don't know exactly the phrase of it is. So we might call it y sub c equals c1 y1 plus c2 y2 plus ... plus cn yn. So this will be the complete solution for the homogeneous one. Next, we'll find any solution y sub p for, I'll have the same equation, so I'll grab it again. Except this time, I will not have a 0 on this side. I'll have some sort of a non-zero function g of x. Then the total collection of solutions for this problem So the total collection of solutions to this non-homogeneous equation will be y sub p plus y sub c. In other words, you'll have a y sub p plus c1 y1 plus c2 y2 plus ... plus c sub n y sub n. And this will represent all of the solutions to it. Now, it should be clear that if yp is a solution for the equation. That means if I take yp and do all of this stuff to it, then it will equal g of x. So if I plug in the whole thing, so if I take, notice this here, if I take the nth derivative and so on. So let me see if I plug this in, a sub n of x. So we'll plug all that in. We'll have y sub p plus, I'll just say y sub c for now, to the n plus dot 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 plus a sub 1 of x yp plus yc prime plus then finally a sub 0 of x times yp plus yc. When you go ahead and do all this stuff, I'll get the nth derivative on this first piece, I'll get the n minus 1th derivative on the next one, etc. You'll see that when I actually do these derivatives, then I'll get y sub p, the nth derivative of it, plus y sub c, the nth derivative of it, plus dot 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 plus a1 of x times yp prime plus yc prime plus a sub 0 of x y sub p plus y sub c. Then all I'm going to do is break it up into a sum of two things, a sub n of x y sub p to the n plus dot 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 plus a sub 1 of x times yp prime plus a sub 0 of x times yp plus, and then I'll have the c portions of all these things. I'll have a sub n of x times y sub c to the n plus dot 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 plus a sub 1 of x y sub c prime plus a sub 0 of x y sub p. Oh, I didn't mean to put that y sub p, I'll put y sub c. Well, we know that anything in the y sub c, if you take away any, just look at just one piece, each of these, when you plug it into the differential equation, will produce 0. So the first piece, the particular solution, will give you your g of x, but the second piece will be 0. So this first part will be g of x, the second piece will be 0, and you'll get your answer, g of x. And then all of these can be are part of the solution since they all zero out. Like anything else, when you integrate something and you get a constant because of integration, that happens because when you go in reverse and take the derivative, the constant disappears. So you put it in there so you represent all possible solutions. Y sub p is called a particular solution. It's one that you plug in and it works in the differential equation. In this example, show that y equals, let me put x cubed plus x plus 1 plus c1 e to the x plus c2 e to the negative x plus c3 e to the negative 2x is a complete solution to y triple prime plus 2y double prime minus y prime minus 2y equals negative 2x cubed minus 3x squared plus 10x plus 4. So remember, there's two stages to this. Since it's non-homogeneous, we have this y is broken into two pieces. We have the y sub p portion of it. That's the particular part, the part without any constants. And over here is the y sub c portion of it. So first, let's make sure that y sub p actually works in there. So let me see if I plug in y sub p, and I'll do all this stuff to it. That will equal, I will replace y sub p with x cubed plus x plus 1. So we're going to have x cubed plus x plus 1, the third derivative of that, plus 2 times x cubed plus x plus 1, second derivative of that, minus, then that thing prime, so I'll have x cubed plus x plus 1 prime, and then what was left there, minus 2y minus 2 times x cubed plus x plus 1. All right, let's go ahead and take some of these derivatives then. I need to take the third derivative. So the third derivative of x and the 1 is 0. The third derivative of x cubed is 6. The second derivative here will give me 6x, and the x plus 1 will zero out again. First derivative in here will be 3x squared plus 1, and then leave the rest of the stuff alone since you're doing nothing to that part. And now just multiply it out and see what we get. So I get 6 plus 12x minus 3x squared minus 1 minus 2x cubed minus 2x minus 2. And let's simplify. I need to get negative 2x cubed minus 3x squared plus 10x plus 4. That's what I need to end up with. Well, good. I have the new negative 2x cubed. So let me cancel that out since I've used it. Then I have negative 3x squared. All right. And then I got plus 10x. Cancel, cancel. And then finally 6 minus 2 will be plus 4. So that checks. There's my YP, a YP. More than one of those could possibly work, but there's one of them. So YP equals x cubed plus x plus 1. All you got to do is find one that works. That's really all that matters. And now for the other pieces, I have to make sure that each of these goes in and makes the equation 0. So let's plug those in. So I need, where's my equation? When we plug in e to the x, e to the negative x, e to the negative 2x into the differential equation, it should be 0. Let's plug those in. So I'll do e to the negative 2x. So I'll do e to the negative 2x triple prime plus 2 times e to the negative 2x double prime minus 2, there was no minus 2, minus e to the negative 2x prime minus 2 e to the negative 2x. So this has to all come out to equal 0, and then I know that this is one of the solutions of the complementary solution. So let's take the, we can do them in reverse order. The first derivative of e to the negative 2x is negative 2e to the negative 2x. Then I'll use that to help me with the next derivative. If I take the derivative of this thing, I'll end up with 4e to the negative 2x. If I take the derivative of 4e to the negative 2x, I'll end up with negative 8e to the negative 2x. And let's see what we have then. I have negative 8e to the negative 2x plus 8e to the negative 2x, so that's pretty easy, plus 2e to the negative 2x minus 2e to the negative 2x. So it does satisfy that. because that equals 0. I will leave it to the student to do the same for either e to the x or e to the negative x. Much easier to differentiate than what I had. Now we have that one last thing we need to do. Let's show that e to the x, e to the negative x, and e to the negative 2x are linearly independent. And so what's good about that then is I will know that my solution is complete, because the most number of these kind of solutions for a third degree differential equation or order 3 differential equation is 3 of them, and I have 3 of them. Let's just make sure they all work. So you remember the Wronskian. How does that work? Well, it's the determinant where in the first column I will start each column with these functions untouched. Now the next row will be the first derivative of all these things. First derivative of e to the x is the same thing. The first derivative of e to the negative x is negative e to the negative x. And the first derivative of e to the negative 2x is negative 2e to the negative 2x. And the third row will be the second derivative of each one of these things. So e to the x, if I take the derivative of negative e to the negative x, I'm back to e to the negative x again. Take the derivative of negative 2e to the negative 2x, and I end up with 4e to the negative 2x. Now I need to remind you how to take the determinant of a 3 by 3 matrix. The way it works is you do something called column or row expansion. So I'll show you what I'm talking about here in a second. I have e to the x, e to the negative x, e to the negative 2x, and e to the x, e to the x, negative e to the negative x, then e to the negative x, negative 2e to the negative 2x, and then 4e to the negative 2x. So what you do, pick a place to start. Now, unfortunately, this doesn't have any 0 entries, and if they did, you would find that doing it along a row or column with multiple 0 entries would be the easiest way to go. I do not have that. So what we do is I am going to operate along the first column of this thing. So this is the things that I operate on. What you do is you start with this quantity, or this e to the x, and you multiply it by another determinant, but a smaller one than you had before. This one, since I'm using this e to the x as my first thing, what you do is you'll cancel out a row, the row that it's in and the column it's in, and the things that are left over will make up the parts of that matrix. So let me have that then. I will then put these in here. Negative e to the negative x, negative 2e to the negative 2x, e to the negative x, and 4e to the negative 2x. Now we know how to do those things, but that's not all there is to it. Plus, then I move down, since I'm going to do this along this column, down here, I made a mistake right off the bat. Minus e to the x. So you take this entry, that'll be, if you will, a coefficient of this determinant. And I play the same game. This time, though, I am going to cancel out the row and the column that it is in and just use like that. If I get rid of the column it's in and the row that it's in, then the 4 entries that I have left surviving all this canceling will be the 4 untouched here. So I'll have e to the negative x, e to the negative 2x, e to the negative x, 4e to the negative 2x. Notice the alternating signs. The next one, same thing, except I'm going to move down to the bottom of the column. This one will turn back to a plus, so you'll alternate plus or minus, plus, minus, plus, minus. And as you might have guessed, I'm going to do the same thing. Let me see if I can, how much of this I can take out of here. And that was negative e to the negative x, negative 2e to the negative 2x. Now I'll x out its column and row. And what I'm left with are these 4 entries. E to the negative x, e to the negative 2x, negative e to the negative x, negative 2e to the negative 2x. It's a time-consuming process, and one that if your calculator can do it for you, that's fine with me. If you have a trick for doing 3x3s, that's fine with me as well. But just note that your trick won't work on anything bigger. So let's go ahead and calculate all of these things. Then this first part here, I have e to the x. And remember how this works. You go and multiply diagonally, like in an x formation. So I'll do this diagonal, negative e to the negative x times 4e to the negative 2x. And I will have negative 4e to the negative 3x. Then you subtract going the other way. So instead of having negative 2e to the negative 3x, I will have plus 2e to the negative 3x minus e to the x times, do the same thing in here. This diagonal way will give me 4e to the negative 3x. And then the other way will give me e to the negative 3x, so minus e to the negative 3x. And then the last one, plus e to the x times, this way I'll get negative 2e to the negative 3x plus e to the negative 3x. Let me simplify everything and see what happens here. When I do all these negative 3x's, I'll get negative 2e to the negative 3x. So I have e to the x times negative 2e to the negative 3x minus e to the x times 3e to the negative 3x. And finally, plus e to the x times negative e to the negative 3x. And then I can simplify everything even further. The first piece will be negative 2e to the negative 2x minus 3e to the negative 2x minus e to the negative 2x. Take these all together and you end up with negative 6e to the negative 2x. And no matter what x is equal to, this cannot equal 0 for any x. So, since it's true for any x, these things are not just linearly independent. This is good no matter what x is. There's not even a finite interval or anything to deal with here. It's all real numbers that this equation is good for. So this solution that we have, this solution right here, is good for all real numbers.